I promised you some theorems, and here they are. They look pretty impressive, all lined up like this, but actually, most of these you know already. The very first one, the one they call the fundamental theorem of algebra. Now, most of you folks have spent at least 2 years studying algebra. This is its fundamental theorem, and you already know it. If the polynomial has a degree of n, then it has exactly n roots. Whatever the degree on the polynomial is, that's how many roots we expect to find. Now they're saying that double roots are going to count twice, and so on. Also, this is going to include imaginary roots in the total root count. The next two go together, and in some textbooks they're listed that way. These are what they call the conjugate theorems, because we're working with square roots. They say that if a plus the square root of b is a solution, then automatically a minus the square root of b will be a solution. They come together. Both the parts of this pair have to be there. And they are identical except for the fact that one's got a plus sign, one's got a minus sign. Now this one obviously is square roots, but this one says a minus b times I. But of course you know that I is the square root of -1. So this really is a square root. And again, they say if a plus b times the square root of -1 is an answer, automatically a minus b times the square root of -1 is an answer. Those two always come together as a pair. So solutions with square roots. I can't promise for any other kind of roots. Come in pairs. That they call the conjugates of each other. Theorem 4. If a polynomial of odd degree has real coefficients, then automatically it has at least one real root, which implies it has at least one x-intercept. They're saying if it's an odd degree function, it has to cross the x-axis at least once. Well, think about it. If we have a cubic function, that's degree 3, and picture its graph. Something like this. With that kind of end behavior, it has to cross the x-axis. There is no way it can avoid it. Whether it wants to or not, it is going to end up crossing the x-axis at least once. Even degree functions don't have to. Like a parabola for x squared, second power. Parabola doesn't have to cross the x-axis. It can float up above it if it wants to. It can cross it if it feels like it, but it doesn't have to. Odd degree functions don't have a choice. Okay, the next one, they say that polynomial in general form, this is a times x to the highest exponent plus b times x to the next highest degree plus c times x to the next highest degree, and the degrees keep going down on the x's until we get all the way to the end to the constant where there is no x term. So we have this standard old polynomial. They're saying that the sum of the roots is going to be the opposite of b over a. It's going to be the opposite of whatever this number is over a. Now you may remember taking the opposite of b over 2a, which gave us the equation for the axis of symmetry on a parabola. This is negative b over 1a. So if this was a fifth degree equation, it would have 5 roots. When you add up all 5 of those roots, it's going to come out to be the opposite of b divided by a every single time. We can also find the product of the roots. For instance, if this was fifth degree, if you multiply out all 5 of them, then that's going to be k over a, the constant at the end, divided by the leading coefficient. Now that's if the polynomial has even degree. It will be the constant at the end over the leading coefficient. If the polynomial has an odd degree, then the product of all the different roots would be the opposite of k over a. So if this one was a fifth degree, you would have to take the opposite of the constant divided by the leading coefficient to find out what the product of the roots is. I wanted to include this one because it's appeared on the SAT. On the multiple choice, they give you a polynomial, ask you to find the product of the roots or find the sum of the roots. And so people factor away, find out what all the roots are, and then they add them all up, and then they have their answer. But it takes much longer than the time allotted, which is about 1 2/3 minutes per problem. So if you know this shortcut, you can just go right to the opposite of b over a for the sum and use the k over a for the product. And they have some examples down here. Gave us a nice normal looking polynomial. This is degree 3, so it should have 3 roots. And they're saying that the sum of those 3 roots is going to have to be 5 over 2, because it would be the opposite of negative 5 divided by 2. The product of the roots, they said, is negative 9/2. Now this is an odd degree function, so we have to take the opposite of the constant and put it over the leading coefficient. So that would be the opposite of 9 divided by the 2. And that's where they get this from. Got a nice normal looking equation right here. And they said the sum of the roots is 0. But it's supposed to be opposite of b over a. Well, this one's a little tricky because this one is missing the cubed term. There is really 0x cubed hidden in here. So b would be 0, and the opposite of 0 divided by 1 is going to come out to 0. It's an even function, an even degree function with highest power of 4. So the product of the roots is just going to be whatever the constant is divided by the leading coefficient. So these look intimidating at first, but they're pretty easy actually, and as I said, you do know most of them already.